Previously, I showed how a web camera could be attached to a Haimer 3D sensor to read its mechanical face. Then with those measurements, construct commands that are sent to LinuxCNC to perform touch-off operations automatically. I've extended that idea by adding a second camera, which is downward facing and identifies holes in parts mounted in the vise. The center positions and diameters of the holes are estimated using this camera, and the estimates are actually pretty good given the low resolution of the camera. But they can be improved by probing each of the holes using the web-enabled Haimer sensor. This combination is really useful for reverse engineering a part or for performing a verification while the part is still mounted. The hardware consists of two web cameras held in place using 3D printed parts. One is attached to the face of the Haimer 3D sensor and the other to the side of the milling machine's head using magnets. Some sandpaper provides grip, preventing the camera from rotating. Ideally, the downward-facing camera is square to the milling machine's table, but the software is tolerant to some amount of error, including this crazy compound angle. Tolerance of the downward-facing camera's position, including height and angle to the table, comes from identifying the corners of the part and then entering its dimensions. The image is then de-warped to make the selection rectangular. A skewed camera will introduce some systematic error because holes will appear oblong. In this case, hole F, which is 900 thousandths in diameter, is estimated to be 30 thousandths smaller, but this is only about 3% error. Of course, any change in the camera's position is going to change the error. It's best to place the camera in a consistent location, estimate systematic error, and then remove it. To learn the accuracy of the vision system, I create a test part with holes of known position and diameter. All the holes are circularly milled to give the best quality hole, except for the smallest, which needed to be drilled. Before locking a probing path, each frame from the downward-facing camera is being analyzed for holes. After all the holes to probe are in view, the corners of the part are selected and its dimensions entered. This creates a table of estimated position and diameter for each of the holes. Until the probing path is locked, it's updated as the mill moves to minimize travel distance. The software integrates the augmented views from both cameras, with the Haimer 3D sensor probe tip shown as a yellow or red circle. The circle is red if the probe tip is below the z equals 0 plane, otherwise it's yellow, and the diameter indicates relative z height. Once ready, the probing path is locked, indicated by change in color. Locking the probing path removes a lot of calculations and allows the frame rate to increase, and a high frame rate is necessary for catching unexpected probing events. I'll show a section of the probing operation sped up 4 times. Probing this entire part takes about 6 minutes without any optimizations. Possible optimization is probing 3 points instead of 4, and this may yield acceptable accuracy, especially if the starting point is close to the hole center. During the development of the software and this video, this part has been probed dozens of times without overshot of the probe. Other than luck, the success comes from moving in small enough increments that a single move will not break the probe, giving the camera's time to stabilize before acting on measurements from the camera and aborting in-progress move operations if the measurements are unexpected. As with any software that interacts with the real world, there have been gotchas, and they probably all have been related to poor lighting or timing. In general, if interfacing with the real world, it's best to eliminate dependencies on or assumptions of timing and act only on what's known from probing and sensing. The software is written in Python and is on GitHub. If you want to browse the code or are brave enough to try this code. There's a little more work that I'd like to do, and please share your suggestions, and especially let me know if you are working on something similar. As crude of an operation as this has been, I think the error terms are pretty good. The probe positions are generally plus minus 5/10, and even the estimates from the camera are often under 5 thousandths. Diameters look good too, with probe diameters plus minus 1,000th. Probe positions and diameters are reasonable for this CNC mill. The diameters estimated from the video show a possible systematic error since all the measurements are similarly inflated. This could potentially be subtracted out. Still, 10 thousandths off on holes between 250 to 900 thousandths is not bad from a 720p image. By repeating the probing operations, we get a sense of consistency, here summarized with standard deviations of position and diameter error. Roughly, we may say that these errors fit a distribution where 68% of the time error relative to the mean will be less than 5/10. Probe diameters have a similar explanation. The main point is that measurements are pretty consistent.